Bismillahirrahmanirrahim. Hello everyone, this is another Seismostruct tutorial. In this tutorial I'm going to show you how to perform a nonlinear time history analysis on an existing or retrofitting concrete or steel structure. In a previous one we had used nonlinear pushover analysis, and we had an existing structure, this one, and also we had some column jacketing in the first and second floor. Then we got this capacity curve. So the structure capacity or response is quite improved. So this is what we call retrofitting or stringing of the existing structure. But in both cases, we can evaluate the performance of each elements, beam column, yielding, crashing, and also fractures. So now what we're going to do is we want to use, instead of pushover, we want to use the nonlinear time history analysis to see how the structure responds. We have choice to model this one, the existing structure, to see, and then we can create some renovation and see the response. So here I go back to the Seismostruct software, and I want to go to the building modeler, because I want to model exactly the previous one. It's called new. And here first, before you come to create the model, and you have to come to here. So in advance you should change the modeling to the dynamic time history, and the control node should be automatic. So what does it mean? When we use the dynamic time history, the program is quite intelligent, and it will detect which node should apply that time history. So this is very important. In case if you select that first floor, second floor, third floor, so the program, that's also up to you, but when you're using automatic, so the program will determine the base of the structure should apply the time history. And also you can change the type of frame modeling. So now here is the frame column beams, and it's called elastic hinge full space frame elements. We have 3 methods, and you can use which one is good for your work. But this method is which called a lumped model, which is the nonlinear behavior is concentrated in the end of beam column. And also the slab modeling, and also the load combination coefficient you can give, and the performance criteria you can give it, check it, this one as well, the shear capacity of the frame, and also the rotational capacity of the beam joint, beam column joint, and also the code based check. So that should check the rotational capacity and shear capacity as well. So I'm going to OK. So the first setting is, now you can change the story I as you wish. But in a previous tutorial we had the same properties. Okay, when create it. When I create here, I will enter to the modeler, and I can model that. So I have already desktop, and here was my AutoCAD plan, and I'm going to here. So the same. If I create existing structure, so the column was 40 by 40, and the beam was 40 by 50, and the slab and infill panel walls, everything. But now what I want to do is, and you can check the previous tutorial and see the existing structure, but I want to, instead of the jacketing, I want to add some brassing. So this brassing is a new method. Instead of using jacketing, we can add some brassing. Even in the brassing, you need to improve the column as well. So what I'm going to do is I can add jacketing, or even I can suppose that's okay, let's have the with the same column. Just that this brassing can get the lateral force, but when the lateral force transfers to the beam column, so the beam column will damage. So it's a little technical parts, and you can retrofit, including adding jacketing for the columns and also adding the brassing. Now you can suppose this structure is already existing. If I consider the same column of existing column and adding brassing, so then you can change the methods. But the main purpose of this tutorial is to how you can evaluate your work on an existing time history record. So I'm going to using selecting here, come to here, geometry, I'm going to 400 by 400. I'm going to quickly model them. So this is the column is created, and now when I have insert brassing or steel brassing, so we have no need to add this infill panel, because in some area we can add the, instead of this infill panel, we can add the load to the beam columns, to the beams. So we not ignore this time. We had the beams. We can come to the geometry and select the proper beam 400 by 5, and here selecting the middle point, and I'm going to select to here to here. So the first floor column is finished. So next I wanna add the brassing. So now here is the brassing. When it comes to here, you will see this figure. So there's no need to see, no need to check it every time. You can. There was when you come back first. Yeah, you can never shoot this again. Okay. Here you can select the middle, and the size of this brassing is 150. You can, it is SH 150, which is the thickness, and the weight and the thickness is 10 milli. You can change using that this box section or hollow section. You can change any section you want. The previous one 115 by 10, which is a square, 100 and just 10. We also have another choice. You can see there is multiple. This is the square one, and this is the another shape. We also have right to use another section as well. So I'm just going to use IP 140. So 140 is okay. And here the type of brassing. So we have X brassing connected diagonals, which means the connection and the diagonal center is quite fixed. And also we have this connectivity, which is the diagonal is passing without connectivity. So you have choice, but using express connectivity is okay. And also the member classification should be as a primary or secondary. And sometimes you have to use secondary as well, so the load transfer to the first, that's primary. Now here the connection is we're using pin because we will use NAT pole connection. Now I can add in the 2-3 inputted locations. So one is here and one is here in the X, and again I want to use one is here and one is here. Now I can go to the 3D and you can see the model is created like this. So now I want to add some slabs, and here the slab thickness is 150, which is as before, and it's the gravity load. Adding this one here, 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 here. Now the first floor is done. I'm going to copy to the second floor and going to copy to the third floor as well. Okay, and I'm going back to the third floor, and I want to add one more slab in the last floor. So I go back to 3D, and you can see this is second floor, and this is the last floor or third floor. Now I can exit the modeler, and the program automatically asks me to save viewer, and I'm called existing bracket frame. In a previous one was infill wall, so this time we used infill bracket. And now it's directed to us to define some accelerogram that you want to apply in this model. So I'm taking the Kobe earthquakes. When you comes to here, and you can define the description, and you can select the first point is from here, and the method is time and acceleration, and it asks me the acceleration column is column 2, and so the curve multiplier, which is G, which should be 9.8 here, and it's okay. So now you can see the graph is here. You also have right to scale it, make it a 1.2, 1.5 to see the response of the structure. So now it's okay, we have created. The good thing is that automatic node created the applied load in the bottom of the structure, so there is no another load in the top. And also the gravity load which we applied in the slab is transferred as a mass to the node of this coil. If you go to the node, and you can see the node location, and also you can come to the applied load, and you can see the acceleration is in the bottom of the each column, and you can see that time history which we already defined, and you can see view that time history, and here is called the time history stage or load cases, which is starting from 0 and end in the 40 second, and it's total 4990 steps, and each step is 0.1 second. You also can edit in case if you want to reduce the time of analysis. You can take 20 seconds or less, or even you can increase it. So we don't have anything else because the program automatically define everything for us, and just you can come to here, you can check based on which code you want, so using the United States code, and it's okay, and just go to the processor and run the analysis. So it asks me to save, and I'll save it. It's called frame. You can existing, or you can give it name as you wish. Save, and it start running. Warning: in the element connectivity model applied pending moment release to inelastic frame made load to convergent difficulty in the medium to high inelastic range area. Are you sure you want to put it in? So this notification is because in this joint, which is brassing, and also we have nonlinear hinges. So that nonlinear hinges, significant nonlinear hinges in that specific joint, which there is the moment release, which cause some instability to the structure. So therefore there will be may not converge. So we can say yes, we want to see the convergence, because when the damage is reached to very large, so the program cannot converge for you. So in that point there will be significant damage, because the capacity of a fixed node and also a pin node is so much. So now there is no problem until 2 seconds, almost 2 seconds. So convergence is okay. So it take a while to finish 40 seconds. So after that it's finished, we will see the result and interpret. Now the analysis completed, and it took 10 minutes 32 seconds. And before we go to the deformation part, let's see here in the output log, and here is those elements which is already reached to the yield, and it's giving us in the time step of 3.61 second. And this element which is column first floor reinforcement strain is reached to this one, which means the yield. And also this one, which is beam, already reached to the yield. Regarding to the previous notification which we got in the moment releasing this point, they said maybe they will not converge. Yeah, the program is trying to use multiple iteration. It reached to the iteration 32, which in the setting was 100. In that specific, which is between 0.1 and 0, it didn't converge. Even the iteration reached 32, and it's called divergence. And the second one is adaptive convergence is occurred. So that convergence means that in that step time, the program didn't solve the specific, didn't solve the elements in that step time. So we can give a fixed connection, then that convergence will not occur. Now we can go to the post-processing, and we can see the result and interpret. So the program become more heavier because it has 4,000, more than 4,000 steps. So it's nonlinear, because nonlinear time history is quite expensive analysis. So it take lots of memories and also graphics of your computer. So now let's see the post-processing will show the deformation with convergence data. You can see here called estimated size of output file is almost more than 7 GB, so it's quite large, and like 7 GB data is loading in the program, so it's taking some time. So now here is the result, and when you come to here, you can see this is the base node, which is the bottom, and you can take the rotation, see the rotation in each step time, or you can go to the second floor, third floor, and you can see the in each step time the deformation shape. So this is not too important, but the only important thing is that we can go to see the performance criteria. So performance criteria are showing us in each specific time, which elements yield and which elements didn't. So when you come to here and you can select the performance, you'll see. So the first part is that yield, and here I want to select just only criteria reached. So other in this period of time, which is the beginning of analysis, so it's not reached. But when we come to here, and you can see in the output of 6 seconds, so there is almost beams, columns already reached to the yield strength. We also can see the crashing of unconfinement. You can just press one. We can check in all step time and see if there is any crashing or not. So but for us that yield strength is okay, so in this step time the most of the beam column is yield, but you can see in case the performance ratio is quite high, then you can see there probably there will be some crashing or some fracture, but we couldn't find that fracture because the time step is quite large, and and it's a little difficult to find it. But most beam column is reached to yield. So this is the performance, and you also can see the stress strain output in each section you want. And this is also the action effects on action effect diagrams, which is the each step time. You can see the moment 2, moment 3, and let me see the force. This is the force, the actual force, and you can see significant actual forces on the we can reduce the scale here, and this is so the beam column. We can here see the actual force is quite large in the brassing element and column. So in the last part, you can go to the global response parameters, and you can check specific columns, beams, everything, and you can see that displacement in that column, rotation in that column, and beam, and you can print it. So let me go to the one of the let's go to node column. This one is called lower parts and the upper part. I'm selecting these two and going to the rotational. So showing just in the graph, it can show you the maximum and also minimum. So let me refresh, and you can see the rotation curve in the specific beam column is like this. So in the bottom is not exist, bottom of 0, and the top is up of the column is this one. We also can see the displacement in that column, and here is the displacement in that column. Now we also have to select, this is the specifying columns, and you can get the top of the structure as well. And as well as we can see the moment in each beam column as well, the acceleration, the is curve, the total inertial damping force, everything. So this is the end of the tutorial. So there's a lot of parameters to interpret with them, and this is the end of the tutorial. If you have any question, please put in the comment and I will find time to answer you. See you next time.